So let's go ahead and look at acids and bases. So after watching this video lecture, students will be able to differentiate between the various definitions of acids and bases and identify the species present in solutions, such as acids, bases, and their corresponding conjugates. So the various acid-base definitions that we're going to be looking at are Arrhenius, Lewis, and Bronsted-Lowry. So let's go ahead and focus on the Arrhenius model. Okay, so the Arrhenius model for acids basically state that H plus ions, or protons, as they will be sometimes called, are going to increase when you place an acid into water. Okay, so if I take something like HCl and I place it into water, okay, what's going to happen is going to disassociate into H plus and chloride ions. So in this context, an Arrhenius acid is going to increase the H plus concentration, or the proton concentration, in solution. Bases, Arrhenius bases, are going to increase the hydroxide ion that is present in solution. Okay, so if I take something like sodium hydroxide, what's going to happen? It's going to disassociate into sodium ion and hydroxide ion, and you're going to see an increase in the number of hydroxide ions present in that solution. Okay, so this is the Arrhenius definition. It's very simple, it's very straightforward. It's not the one that we'll typically use to define things. We're going to actually be focusing mostly on the Bronsted-Lowry. However, we should be familiar with Arrhenius's approach. Okay, so the Lewis model, which is one that actually won't show up on the AP exam, but we're going to be sharing it anyway. The acids from the Lewis model are going to be known as electron acceptors. Okay, and the bases are going to be electron donors. Okay, and so the Lewis model is really helpful when you don't have protons or hydroxide ions to be donating to the solution. Okay, so an example or setup for Lewis acid-base model would be the following. So in this case, we have ammonia. Okay, the electrons here are going to be donated to the boron in this BF3, and you're going to form this compound here. So basically, your NH3 here is going to be acting as your base. Okay, it's going to be donating electrons to the acid, which is your BF3. Okay, so this is my base, this is my acid. Okay, and this is the product that you would get. So the Lewis model, as I said, is not going to show up on the AP exam, but we should be familiar with the different definitions. Okay, and so the last model that we're going to be looking at is the most useful. The Bronsted-Lowry model allows us to explain various different types of acid-base chemistry, and it's very straightforward. So we're going to be focusing on this definition for the remainder of this unit. Okay, so Bronsted-Lowry acids, okay, are going to be proton donors. And the bases, the Bronsted-Lowry bases, are going to be proton acceptors. So guys, remember when I say protons, remember I'm talking about H plus. Okay, I'm not talking about the subatomic particle that's present inside the nucleus of atoms. Okay. So now that we've looked at all of our models and we're familiar with them, let's go ahead and focus on the proton transfers and accepting of protons from Bronsted-Lowry acid and bases. So let's go ahead and let's look at the acid-base proton transfer associated with the Bronsted-Lowry acid and base. Okay, so in this context, hydrochloric acid is our acid, H2O is going to be behaving as our base. So what's going to be happening here is that my HCl is going to be donating a proton to my base, H2O. Okay, so what will happen here, guys, is that this H plus ion will come over here and get picked up by the H2O molecule. Okay, so my acid, okay, we got our base here. Okay, and that's going to give us this product here. Okay, so notice my base picks up a proton and becomes this H3O plus ion, which is known as the hydronium ion. We'll talk about that in a little bit. And of course, there's this leftover chloride from the HCl that gave up the hydrogen, or the proton, excuse me. So remember, acids, according to Bronsted-Lowry, are proton providers or proton donators. Bases are proton acceptors. On the previous slide, we went ahead and we identified our acid and our base. Okay, so our proton donator and our proton acceptor. However, we really didn't have names for the things on the right-hand side. Well, these things over here, whenever you have a transition or transfer between an acid and a base, you're going to end up with products known as conjugate acid-base pairs. And these are molecules or ions that are related to each other based on the gain or loss of protons from that acid-base transfer. So your conjugate acid, guys, is going to be the substance that's formed when a base accepts a proton. Okay, and your conjugate base is going to be the substance formed when an acid donates a proton to another molecule. Okay, so let's go ahead and let's analyze these products over here and decide which one is going to be our conjugate acid and which one is going to be our conjugate base. Okay, so if we start with our conjugate acid, what's going to happen is that the conjugate acid is going to be formed when the base accepts a proton. So this is my base. H2O accepting a proton is going to generate the conjugate acid. Okay, so H2O plus an additional hydrogen in this context is going to give me this ion right here, which is known as the hydronium ion. Again, we'll speak about that in a little bit, but this H3O plus ion, this hydronium ion, is the conjugate acid that is generated from the acceptance of a proton by my H2O base. Okay, so conversely, if we go ahead and we look at our conjugate base, obviously our conjugate base is going to be basically what's left over after our acid transfers its proton. Okay, so this proton got transferred, so chloride is what's going to be left over on this side. So this is going to be my conjugate base. Okay, now another way to think about conjugate acid and conjugate base is to look at this reaction in the reverse. Okay, so the reverse direction. So if I were to look at these two and try to decide which one is an acid and which one is a base, well, the one that has protons is going to be the thing that's an acid. The thing that doesn't, obviously, has to be the base. Now, that's not to say that that definition works perfectly all the time, but it's just another way to kind of look at this conjugate acid-base pairing process. Indicated that we're going to discuss hydronium ions. So basically the hydronium ion, guys, is that H3O plus ion that we've seen on the right-hand side multiple times. Okay, so the hydronium ion basically gets produced anytime you put an acid into solution. Okay, and if that acid gives up H plus ions, it's going to transfer onto the water molecules. Now, the main thing to come away with, guys, is that the H plus ions that are coming from an acid, as we see this dissociation here, are never actually going to move independently. So that means that this diagram or this equation here is not completely accurate with respect to what's actually existing in solution. The reality of it is that this is the more accurate description of terms of what's happening, because this H plus ion is being transferred to the water to produce the hydronium ion. Now, in all practical purposes, H plus is going to be the same thing when we are discussing acid and base chemistry. Okay, so when we go to calculate pH, for instance, okay, we use the hydronium ion concentration to calculate that, but we could also just as easily write this equation with the H plus ion because basically they mean the same thing, right? Because the amount of H3O plus ion is dictated by the H plus that is being released by the acid. Okay, so just so you know, the hydronium ion actually always exists in solution if there's an acid present, so just make sure that you guys have that in your head. So water is kind of unique in that it is known as an amphiprotic substance, okay? So we know that water has basically this structure. Obviously, it has the presence of hydrogens, and it also has locations where it could potentially pick up additional hydrogen ions, and form that hydronium ion. Okay, so we've seen this several times here, okay, where we have HCl interacting with H2O to give us the chloride ion and the H3O plus. In this particular situation, my H2O is acting as a base. Why? Because it's accepting the proton from my acid, hydrochloric acid. Okay, so in this case, H2O is behaving as a base. So if we go ahead and we look at the next example here, we still have water in this example, but we have a new substance. We have ammonia. And ammonia, guys, is known as a weak base. Okay, so if ammonia is a base, that means that our water has to behave as an acid. So in this context, guys, the acid is going to transfer a proton to the base, okay? And so basically one of the hydrogen atoms in the water molecule is going to leave as a H plus ion, okay? And you're going to end up with a hydroxide ion, and NH4 plus as your two products that you get on the right-hand side. Okay, so water is known as being amphiprotic because it can either act as an acid or a base. Now, there are other substances that can go either direction as well, but water is the most prolific. Okay, so for the past several slides, obviously I've been providing you guys with your products, and we need to actually talk about how to approach and how to basically figure out our acid-base conjugates that we will obtain on the right-hand side. Okay, and part of this is actually knowing our various acids and bases. Okay, and so I'm going to give you guys a list of acids and bases to memorize, and you guys will be working on that a little bit later, but as you use this, obviously you're going to get accustomed to it. So on the last slide, we talked about ammonia being a base, right? Okay, so NH3 being a base. So in this context, that's still true. Now right here, guys, this is acetic acid. Okay, and this is related to one of the ions that you guys were supposed to memorize. Okay, one of those 85 ions. Remember your acetate ion. Okay, well, your acetate ion with an additional H plus gives you the acetic acid that you see here. Okay, so acetic acid, we know that acetic acid is going to behave as an acid, so it's going to give up a proton to your NH3. Okay, so what we're going to produce here on the right-hand side, obviously, is our acetate ion, okay, and NH4 plus. Okay, and so if we just follow the protocol of what happens with the base and the acid in terms of proton transfer and acceptance, we'll get our correct products. Okay, now let's go ahead and let's identify our conjugates as an acid or base. Now remember, our acid, our conjugate acid is going to be the resultant product from whatever happens or whatever forms when the base accepts a proton. Okay, so NH3 is going to accept a proton and become NH4 plus. So this is going to be my conjugate acid, right? And obviously the leftovers of the conjugate, or sorry, the leftovers of the acid transferring its protons are going to give you your conjugate base. Okay, so if we repeat this process down below for our HF, remember HF, this is going to be our acid. Okay, water in this case is going to behave as a base. Okay, so we're going to end up with H3O plus and F minus. Okay, so this is going to be my conjugate acid, conjugate base. Okay, so simple, straightforward, and basically that's the thought process behind each of these. Okay, so if we do a little bit more practice, couple more examples, they want us to basically figure out the conjugate bases or conjugate acids for the examples below. So in this first row, we're going to be looking at the conjugate bases. So HCl is an acid. So the conjugate base is going to be whatever is left over after it gives away its H+. So Cl- in this case is the conjugate base. Okay, so in the example of this ion here, if it gives away its proton, you're going to get SO4 2-. Okay, and if this acid or this behaves as an acid, my conjugate base is going to be NH3. Okay, so now that we've determined each of the conjugate bases from the acids above, let's go ahead and let's do the reverse process. So basically they've indicated that we have bases here and they want us to determine the conjugate acid. Okay, so assuming that only one proton is picked up, in each of these cases the bases are going to take on a proton. So remember, the protons have an H+ charge, so our carbonate ion is going to become bicarbonate. Right, notice the charge change. Now we've added an H+ ion. Okay, in this example, we're going to pick up a proton. The acetate ion is going to pick up a proton and give us acetic acid. Okay, and of course, in the case of NH3, we're going to go to the ammonium ion. Okay, so basically, you need to think about what the formation of the conjugate base means relative to the original acid, and you need to think about what the formation of the conjugate acid means relative to the original base. And if you guys can do that, you'll be fine at predicting your products for acids and bases.